Hello everyone, my name is Nikhil Gupta and today I will be talking to you about how to build and tune your deep learning models effectively. Alright, so this is a brief overview of the agenda. First, I'm going to talk about setting up deep learning models. Specifically, I'm going to talk about learning rate, input and batch normalization, and optimization algorithms. These three topics are going to cover about 20 or 25 minutes. In a second video, I'm going to cover activation functions and weight initialization. So if you have limited time, you can watch the first video, but if you have more time, you can go on to watch the second video, which builds upon the concepts learned in the first video. At a later date, I'm going to release another video which talks specifically about bias variance trade-offs as they apply to deep learning models. And here we'll cover topics such as building a bigger network to resolve high bias issues, as well as topics like regularization, early stopping, and collecting more data for resolving high variance issues. Alright, with that, let's move on to the first topic, which is learning rate. To understand learning rate, we need to first understand gradient descent. Gradient descent is an optimization algorithm that is used to find the global minima of any function with respect to its inputs. Specifically for deep learning, we are talking about optimizing the cost function with respect to the weights of the deep learning algorithm. Now the cost function could be either the root mean square error for a regression problem, or it could be accuracy for a classification problem. And the job of gradient descent is to find the weights that are going to minimize the loss or the difference between the model's prediction and the actual data that is used for training. Now to understand gradient descent in deeper detail, let's take this simple example. Let's assume we have only one weight represented by omega, and the initial value of omega is omega star, and we have a cost function j omega which is represented on the y-axis. Let's assume our initial data point is right over here, and our global minima is over here represented by the orange dot. To go from the initial data point or initial weight to the global minima, essentially gradient descent moves in the direction of the negative gradient. Now what does that mean? The gradient at any point represents the rate of change of the cost function with respect to the input. So for example, if we draw the tangent at this point, this represents the gradient at this specific point. So we can see as we increase omega, the cost also increases. So the gradient in this case is positive. And in order to move from this point to the global minima, we actually have to reduce the weight. So when the gradient is positive, we have to reduce the weight to reach the minima. Similarly, you can see if our initial point was over here, then the gradient is like this. The gradient in this case is negative, because when we increase the weight, the cost will actually decrease. So the gradient is negative, but in order to reach the minima, we actually have to increase the weight. So again, the gradient is negative here, and we are going to increase the weight to reach the global minima. So the idea is to move in the direction opposite to that of the gradient, and that is what is represented by this equation here. So the new weight is equal to the old weight minus the gradient of the cost with respect to the weight. You will also notice that you have this term alpha, and alpha is actually what is the learning rate. This is a hyperparameter used during the training process, and this controls how large or how small of a step the gradient descent algorithm will take between iterations. So if you have a very large alpha value or very large learning rate, your gradient descent algorithm will move very quickly towards the global minima. But the disadvantage is that there's a tendency to overshoot the minima. So the gradient descent algorithm might be going back and forth around the global minima without actually converging to the global minima. On the other hand, if you use a smaller learning rate, then you might converge to the global minima, but because you're taking smaller steps, you might take a very long time to reach the global minima, and your training time might increase substantially. And in fact, learning rate is one of the most important parameters that you can tune to build a deep learning model effectively. Okay, so here we have an animation showing the effect of learning rate on the training process. So our data set here is linear, so we have y which is linearly changing with respect to x. In the first case, we have a learning rate of 0.01, which is rather small for this case. And you can see that even though the algorithm is converging towards the global minima marked by this x, the algorithm is taking a long time to do that. There are several iterations that the algorithm is taking. In the second case, we have a slightly higher learning rate of 0.1. And in this case, you can see that the algorithm is taking very few steps and converging to the global minima really quickly. And we can see the final solution over here. In the third case, we have a very high learning rate of 0.99. And in this case, you can see that the algorithm is actually bouncing off the walls of the cost function before it eventually reaches the global minima. But it's taking many more iterations to do that. And finally, we have a fourth case where the learning rate is so high that the algorithm is actually diverging away from the global minima. So in this case, it won't even converge towards the global minima. Typically what people do is they start off with a very high learning rate, and as the number of iterations increase, that is as they get closer and closer to the global minima, they will start to reduce the learning rate. This is a fairly common practice that is used in deep learning. Now, one of the more recent developments is this idea about cyclical learning rates. In the previous slide, we saw this idea of starting with a very high learning rate so that we can quickly start moving towards the global minima. And then as we move towards the global minima, as we reach closer, we start reducing the learning rate so that we don't overshoot the global minima. Now, the idea of cyclical learning rate is actually to increase the learning rate for some time and then decrease it and keep doing that again and again. And this idea is to overcome the problem of saddle points. So typically, if you look at deep learning models, the cost function looks something like this, where you have local minimas, but you also have these saddle points, which are regions where the cost function does not change much with respect to the weight. So if you look at the gradient at these points, the gradient of the cost function with respect to the weight is very low. So the algorithm is going to take very small steps once it reaches these points. Now by increasing the learning rate, you can actually overcome these saddle points very quickly, because if your learning rate is higher, you can actually jump across this saddle point much quickly and reach the global minima faster. That's the whole idea about cyclical learning rates, and it's fairly new. And there's a small variant of that called fit1 cycle, where you only do this once during your entire learning process. And this is a very fast and effective way to reach your global minima faster. So these are the takeaways from learning rate. Typically, you want to start off with a fairly large learning rate so that you can quickly start converging towards the global minima. Then as you get closer and closer to the global minima, you want to reduce your learning rate so that you don't overshoot the global minima. If during the training process you find that your training is taking a long time, it probably means that your learning rate is too small and you can afford to increase the learning rate to reduce the training time. On the other hand, if you find that the accuracy is low, it probably means that your learning rate is too high and your algorithm has overshot the global minima. So in this case, you want to reduce your learning rate. And how do you find the optimal value of your learning rate? Typically, you can use a grid search, where a random grid search is preferred over a predefined grid. But you can also use more optimized techniques to find the optimal value, for example, by using Bayesian optimization to find the right hyperparameter value. And like I explained previously, a newer concept is that of cyclical learning rate, where you both increase the learning rate for a short amount of time and then you reduce the learning rate. And this helps you overcome the problem with saddle points. Okay, so let's move on to the second topic, which is input and batch normalization. To understand why normalizing inputs is important to train a neural network, let's take a look at a very simple example where we have two weights, W1, which varies from 0 to 10, and W2, which varies from 0 to 1. What you will notice here is that the gradient along W2 is much larger than the gradient along W1. So in order to optimize this accurately, you want to use a smaller learning rate along the W2 direction, but a larger learning rate along the W1 direction. Now, why is this the case? Along the W2 direction, you want to take a smaller learning rate because you want to prevent the optimization from bouncing off the walls of the cost function. On the other hand, you want to take a larger learning rate along W1 because you want to converge quickly towards the global minimum. Remember, the gradient over here is smaller, so that's why you want to take a larger learning rate. Now, if you look at the equation, the weight update equation, what we realize is that although the gradient with respect to W1 and W2 is different for the two weights, the value of alpha is actually the same for both. So we cannot use a different alpha for this direction for W2 and for W1. So how do we actually resolve this conundrum? The solution is very simple. You would normalize your inputs. So basically both your weights W1 and W2 would be on the same scale, typically 0 to 1. And now because your weights on the same scale, you can use the same value of alpha to optimize the algorithm, and your algorithm will actually take much fewer iterations to reach the global minima. So this is an important step in order to make sure your training process is sped up. Okay, so in the previous slide, we saw that we want to normalize the inputs going into the neural network in order to speed up the training process. But what about the hidden layers? If you look at the structure of a neural network, the output of the first hidden layer acts as an input to the second hidden layer, and so on and so forth. The weights of the hidden layers are actually being updated in every iteration. So it just so turns out that the second hidden layer might actually see very different values of the inputs between iterations. And this is the same problem that we saw previously with the input vectors x in the previous slide. So this idea is called the covariate shift, wherein the inputs can vary between iterations, and this actually tends to make it harder for the optimization algorithm to converge to the global minimum. The solution is actually fairly intuitive and simple, which was proposed by Google in 2015, and the solution is to normalize the inputs going into the hidden layers similar to what you would do for the input layer. So the process of normalizing the inputs going into the hidden layers of a neural network is called batch normalization. And what you see here are the results from the paper from Google. It is showing the comparison of two models built on the MNIST dataset. The first model shown in blue is with batch normalization, and the second model shown with the dotted black line is the model without batch normalization. And you can see that for the most part the accuracy is similar in both cases, but the model with batch normalization takes much less number of iterations compared to the model without batch normalization. In figure B, we can actually see the distribution of the weights of the hidden layers, and we can see that initially the distribution varies a lot, and this actually slows down the training process, and that's why it requires larger number of iterations to reach the global minima. On the other hand, with batch normalization, which is figure C, we can see that the distribution remains fairly stable, and because of this, the global optima can be reached much quicker through the gradient descent algorithm. So here are the takeaways from the normalization process. First, you would normalize the inputs going into the first layer of the neural network. This will help make sure that your weights for the first layer are of the same range, and you can use the same value of alpha for all the weights. And this helps ensure that your training process reaches the global minima in the fewest number of iterations. A similar concept can be extended to the hidden layers of a neural network, where you would normalize the inputs seen by the hidden layer. And this process is called batch normalization, and typically you will see this batch normalization being added to all the hidden layers in your neural network. With that, let's switch gears a little bit and talk about the third topic, which is optimization algorithms. So we've already spoken about one kind of optimization algorithm called gradient descent, wherein the algorithm will process all the data, compute the cost function, then compute the gradient of the cost function with respect to the weights, and then update the weights to go on to the second iteration. The problem with this approach is that the algorithm has to process all the data from one iteration to the second iteration. And because the data can be very large for a deep learning model, this process is extremely slow. The other extreme is what is called the stochastic gradient descent, wherein you only process one data point in every iteration. And because you're processing only one data point, the time taken for every iteration is lower, but the disadvantage is that the algorithm becomes very choppy and noisy because you're only processing one data point. The other disadvantage with this process is that you cannot take advantage of vectorization. So the way the memory is set up on a GPU or a CPU, the time taken to process, let's say, 64 or 128 observations is almost identical to the time taken to process one observation. So a happy medium between these two algorithms is what is called a mini batch gradient descent. So in a mini batch gradient descent, you don't process the entire data set between iterations. You don't process just one data point between iterations, but rather you process about 64 to 128 observations between iterations. So the process becomes less noisy compared to the stochastic gradient descent, but it becomes faster compared to the gradient descent. So it's a happy medium between the two algorithms. And this is what is typically used for training deep learning models. Now this is not without its problems, right? So the algorithm is still noisy. So to overcome the noisiness of this algorithm, we use something called momentum. Alright, so to understand momentum, let's take a look at gradient descent once more. So this is the typical flow for gradient descent. So at the first iteration, we might have a gradient pointing in the upward direction, so it will make a step in that direction. In the second iteration, we might have a gradient pointing in the downward direction, so it will take a step in that direction, and so on and so forth. So in this case, we can see that the gradient is actually alternating, and the optimization algorithm is actually bouncing off the walls of the cost function as it approaches the global minima. And as we've seen previously, this is the exact situation where we want to avoid, because it increases the number of iterations required to reach the global minima. Now what you will notice intuitively is that if I were to take the average of the first and the second gradient, then they would tend to cancel each other out, and what I would be left with is a gradient which is pointing more in the direction of the global minima. Similarly, if I were to take the second and the third gradient and average that out, I would again be left with a gradient which is again pointing more in the direction of the global minima. And by doing this repeatedly, I can actually reach the global minima much faster because the gradient is now pointing more in the direction of the global minima. And this is the exact idea behind momentum. So if you look at the equation for gradient descent that we had seen previously for the weight update, we have the weight W, the new weight W is equal to the old weight W minus alpha times the gradient of the cost function with respect to the weight. So for simplicity, I'm going to represent this gradient by this term called dW. So in momentum, this equation is slightly modified. We still have the new weight equal to the old weight, but instead of using the gradient, we are going to use this term called velocity, VDW. And this VDW term is nothing but a combination of the velocity at the previous iteration of the gradient descent plus the gradient at the current iteration. So these two factors are combined to form the velocity at the current iteration, and they are both weighted by the term called beta and 1 minus beta respectively, where beta is the hyperparameter for this momentum algorithm. Now this might sound a little bit ominous right now, but let's take a look at a simple example. So we start off by initializing the velocity to 0. Then at the first iteration, we have the velocity is equal to beta times the velocity at the previous iteration, which is VDW 0, plus 1 minus beta times the gradient at the current step, which is dW1. Now we continue doing this process for the second iteration. We get VDW2 is a factor of the gradient at the previous iteration plus a factor of the gradient at the current iteration. So now this starts making a little more sense, right? So the velocity is a combination of the gradient at previous steps as well as the gradient at the current step. Of course, both are weighted differently, but we'll come to that in the next slide. Similarly, at the third iteration, VDW3, now we have this velocity is a combination of the gradient at the first iteration plus the gradient at the second iteration plus the gradient at the third iteration. So again we can see that the velocity is a averaging effect of the gradients of the previous iterations as well as the current iteration. Okay, so I've copied over the equation for the velocity at the third iteration from the previous slide, and like we saw previously, it consists of terms from the gradient for the first iteration, gradient for the second iteration, and gradient for the third iteration, and they are all weighted differently based on the hyperparametric beta. Now typically the value of beta is between 0 and 1, and what you will observe is that if I were to use a lower value of beta, let's say a very small value, then the term beta square would be even lower, right? That would mean that it's going to weight the earlier gradients much lower compared to the later gradients. On the other hand, if I were to use a very large value of beta, then the beta square term would be very close to 1, and that would mean that I would weight the previous gradients much higher compared to the more recent gradients. So this is a basic observation, and what you will also observe is because we are multiplying previous gradients by square terms, cube terms, and so on and so forth, it's essentially an exponentially weighted moving average of the gradients. Now practically the value of beta that is used is between 0.8 and 1, and the default value you will find in many frameworks is 0.9, and this is rarely changed for optimizing your training process. 0.9 typically works for most deep learning training processes.
So another optimization algorithm that you will typically see in frameworks is called RMSProp. And to understand RMSProp, again, let's look at gradient descent first. So we've seen previously the case where the inputs were not normalized. So if you look at that example again, we have two weight vectors. Along the horizontal axis, we have a weight vector which has a higher range. Along the vertical axis, we have a weight vector which has a lower range. And the gradient along the vertical direction is much higher compared to the gradient along the horizontal direction. So typically we want to take a smaller step along the vertical direction and a much larger step along the horizontal direction. But as we've mentioned previously, we can only use one alpha value for all the weights. So RMSProp was used to solve this problem, wherein the weight equation is again modified slightly. So we have the new weight equal to the old weight minus alpha times the gradient at the current iteration divided by the square root of STW. So what is STW? STW again is a weighted factor of the STW at the previous iteration plus the square of the gradient at the current iteration. So now we are taking the square of the gradient term and averaging that out over multiple iterations. Okay, and we can see along the vertical directions, because we have a larger gradient, the STW term along the vertical direction will be much higher. So when we update the weights, because the STW term is in the denominator, we will take a much smaller step in that direction. Similarly, on the horizontal direction, because the gradient is much lower, the STW term is going to be smaller. And again, because this is in the denominator, the step that we will take is going to be much higher. Now, a practical consideration here is that we are going to add a small term called epsilon to the denominator, because STW can actually be 0 and we want to avoid divide by 0 errors. Okay, so to summarize, the weight update equation for RMSProp is given by the equation in the box, and the STW term is the average of the square of the gradients of previous time points and the current time point. Beta 2 and epsilon are hyperparameters to this RMSProp algorithm. Again, similar to what we saw in momentum, the beta value is between 0 and 1, and the epsilon value is very close to 0. It's a very small value. We don't want to add a very large value to upset the algorithm, but we do want to make sure that we don't divide by 0. So that's why we use a very small value for epsilon. And similar to what we saw previously for momentum, we are essentially in this case taking the exponentially weighted moving average of the square of the gradient in this case. In case of momentum, we took the exponentially weighted moving average of the gradient. In this case, we are taking the average of the square of the gradients. And similarly, if we use a higher value of beta 2, we are giving a lower weightage to recent gradients. If we use a lower value of beta 2, we are giving higher weightage to recent gradients. For practical purposes, beta 2 value is typically 0.99 or 0.999, and these are default values that come in many of the frameworks, and typically these are not changed to improve the algorithm. These values work fairly well. And similarly, epsilon is the default value is 1e minus 8, and again rarely changed to improve the algorithm. So the next optimization algorithm that we will look at is called the Adam optimizer, which is one of the most popular optimization algorithms that is used in deep learning. The intuition behind Adam optimizer is to combine the momentum and the RMS prop algorithms into one algorithm. So here we have the equations for momentum and RMS prop that we've seen in previous slides. In momentum, we have this velocity term VDW, which is the exponentially weighted moving average of the gradients at the current time point and the previous time points. In case of RMS prop, we have this term called SDW, which is the exponentially weighted moving average of the square of the gradients. And the weight update equations are given by these two equations shown on the right. In case of Adam optimizer, we actually use the same equations for VDW and SDW, but the weight update equations are modified to take both of these into account. So we have the new weight equal to the old weight minus alpha times the velocity divided by the square root of the SDW term. So in actual implementation, there is something called bias correction which is implemented. So what happens is when the algorithm is just starting off, it doesn't have enough history or enough previous gradients to make a decision. So that's why you have to correct for that, and that's what is called bias correction. So that's something you might see in when you're going through the literature for Adam optimizer, and that's what it's basically taking care of the initial few gradients when you're just starting off the optimization algorithm. And another tidbit of information is, so Adam is not the name of a person, it actually stands for adaptive moment estimation. And the reason is that the term dW, which is the gradient, is called the first moment, and the square of the gradient, dW2, is called the second moment. And hence this algorithm is called adaptive moment estimations, because you're adapting the weights based on the moment estimation of the gradients. Okay, so we've taken a look at several different optimization algorithms. So what are the takeaways? So takeaways are that typically we will use mini batch gradient descent rather than using batch gradient descent or stochastic gradient descent, because that tends to speed up the optimization process and we reach the global minimum much faster. In addition, we use advanced optimization algorithms rather than using stochastic gradient descent. We use advanced algorithms like Adam optimizer, which tend to perform much better for deep learning models. The hyperparameters for Adam optimizer are alpha, beta 1, beta 2, and epsilon. Alpha, which is the learning rate, is one of the most important parameters. We typically tune this to get the best performance from the model. Beta 1, beta 2, and epsilon have default values of 0.9, 0.999, and 1e minus 8 respectively, and these are rarely changed when we want to improve the performance of the optimization algorithm. Typically, alpha is what is changed to improve the performance, not beta 1, beta 2, or epsilon. Okay, so that brings us to the end of the first part of the presentation. In this part, we covered three main topics. We talked about learning rate and how this is one of the most important parameters that you can tune to improve the performance of your deep learning model. We talked about some new techniques such as fit1 cycle, which help to improve the performance even more. Then we went on to talk about the second topic, which was input and batch normalization, and why this should be used to improve the training speed of your algorithm. And finally, we talked about several optimization algorithms and concluded that Adam optimizer is one of the most popular algorithms for optimizing that is used for deep learning and actually works very well for many different applications. In the next part, we will cover two more topics, namely activation functions as well as weight initialization. So with that, I'll see you in the next part.